The homework isn't a perfect reflection of where you are right now, but I think it'll help us if, even today, if we go through, as we go through the practice problems, if you have an epiphanal moment, you can look at the, your homework that I returned back to you, and you can see where you don't track with the way it should have been done, and you go, oh, that's what I should have done, and maybe even work the problems again, or do the on your owns again, or go to the extra practice problems in the back and do them again. And if we get through the practice problems today, which I'm not sure we will, but if we do, then we can go through some extra practice problems tomorrow. So if you don't have any questions for me, but you do know some areas that you're struggling, I'd recommend that you go ahead and choose an extra practice problem from the appendices in the back of the book for Module 2. Pull out a couple questions, say, you know what, let's work this one again. I think I get this one, but let's see if you work through the problem one more time. Let's see if I can finally nail down that I understand the concept before Thursday, before we take the exam, okay? So that's what today is for. Today is in search of an epiphanal moment. Not for everybody, just for a few people. It is, to be honest, it is kind of discouraging when I'm doing looking at the homework and a question says we want to make a kilogram of something and it's made up of these two components. How much of each do we need? And you just go, oh, 500 grams of each. Yeah, 500 and 500 makes 1,000. Yeah, but they don't mix gram to gram. There's a ratio there, right? Remember the whole thing about making batches and coming up with the coefficient so that we can multiply by how many batches we're going to make? I need to make 10 cakes. Cakes have eggs and flour in it. I'll put in 10 eggs and 10 cups of flour. Why? 10 and 10. Make it even. That's going to be some pretty nasty stuff. So you have to follow the recipe. And that's the kind of thing today. But, oh, on the homework, I put 500 of each because conservation of mass is 500 plus 500 is 1,000. Yeah. But what you're going to end up with is the analogy of the brownies with a bunch of baking soda piled up on top of it. It's not the right recipe. So I think the best way to find out if you have, either you understand the concept or you have come to understand the concept since you did the homework, is for us to just walk through and work through the problems together. So go ahead and look up practice problem number 1. That's where we're going to begin. I'll try to keep all my little pieces of notes up here together as we go through. Practice problem number 1, module chapter 2. The question reads that a chemist uses an experiment similar to the experiment in 2.2, okay? But that's really not that significant. That's not important. It's just they're going to decompose 150 grams of water. And when he decomposes the 150 grams of water, he finds that he makes 16.7 grams of hydrogen. How much oxygen must he have produced? So 150 grams of water decomposes. That's the reaction arrow. I said this is one of the kind of reactions we're going to learn, decomposition. We've talked about it a lot because that's how we've come to understand what an atom is, right? We've taken compounds and broken them down until they can't break down anymore and say, hey, if it can't break down anymore, that's an atom. And what's an atom structure? The atom is made the element is made up of an atom. Break it down as far as I can. It's an element. Elements are atoms. Okay. 150 grams of stuff. Just think about the general principle. 150 grams of stuff produces 16.7 grams of stuff and some additional stuff. How much of the additional stuff must have been produced? It's a law of mass conservation, right? Or conservation of mass. I don't create or destroy any mass, any matter. Therefore, I must start and end with the same amount. If I have 150 grams to start with, how much must I end with? 150 grams, right? I can't make or destroy. I can only rearrange. So if I have 150 grams of Legos and I take them and I build things out of them, how many grams of Legos do I have? I still have 150 grams of Legos. All I've done is rearrange them. So the general law of mass conservation says that the mass of the reactants has to equal the mass of the products. So to figure out what this unknown amount is here, which we come out to figure out is 133.3 grams. How do we know that? Well, 150 grams has to equal 16.7 grams plus however many grams of oxygen. And by subtracting 16.7 from both sides, we see that the grams of oxygen are 133.3. So the reaction looks like this. 150 grams of water decomposes into 16.7 grams of hydrogen and 133.3 grams of oxygen. Now, I told you before that the question here just said hydrogen and oxygen. And at where you're at, if you just put H or O, or if you wrote oxygen or hydrogen, that's fine. I know, for example, that hydrogen, mentioned this yesterday, that hydrogen exists not as atoms of hydrogen, but as molecules of hydrogen. So I know that it's not going to be H, it's going to be H2. Don't worry about it from where you're at right now. Same thing with oxygen. It's also a homonuclear diatomic, which means it's always in the form of a molecule. So if you just had H and O, that's fine. The principle here is the law of mass conservation and how to figure out the missing piece. 150 grams equals 16.7 grams plus what? Figure out the what. And that's all practice problem number 1 was trying to get you to do. So any questions on, yes ma'am?
So do we not have to worry about the significant figures in that one? Because like the 16.7 is 3 significant figures and then 133.3 is.
Because it's subtraction, it's precision.
Okay.
So it's precise to the 10th place. So you do need to worry about precision, not significant figures in that way. If we're doing multiplication or division, yeah, sig figs. Addition and subtraction, look at precision. And that's why my answer has to be to the 10th place. If it was a nice even number, it would be 133.0. This 0.0 would need to be there because I need to be precise to the 10th place. Okay. Any other questions on number 1? Number 2 says that to burn a piece of wood, oxygen gas has to be added, and ash, carbon dioxide, and water are products of the burning process. So we're taking wood and oxygen, and in that reaction, the burning process, that's a reaction, produces water, ash, and carbon dioxide. If 3.8 kilograms of oxygen gas is used to burn a piece of wood, then what was the mass of the wood if the chemist collects 3.12 kilograms of water, 925 grams of ash, and 15.14 kilograms of carbon dioxide? Do you see that this is the same principle as the last problem? This is another law of mass conservation, or conservation of mass. So what we're actually driving to is saying, okay, I know that this and this produce these 3 things. So the mass that I start with has to equal the mass that I end with. How do I determine the mass of what I started with? Because the mass of what I started with is the mass of the wood plus 3.8 kilograms of oxygen. So I need to subtract out the mass of the oxygen from both sides. See? If I subtract 3.8 kilograms from the reactants and from the products and solve for the unknown, which is the mass of the wood, the math looks like this. See, the 3.12 kilograms plus, and I convert this to kilograms, 0.925 kilograms plus the 15.14 kilograms. So add those numbers up, all in units of kilograms, minus 3.8 kilograms. This 3.8 was the mass of my oxygen. It was one of my reactants. So I need to subtract it from the reactant side and subtract it from the product side. And that's what the math looks like. Again, the principle is the mass of the wood plus the mass of the oxygen has to equal the mass of the water vapor plus the mass of the ash plus the mass of the carbon dioxide produced. Solving for the unknown mass of the wood. Here's another example using addition or subtraction where we have to take it to which place. I have an answer that's precise to the hundredths place, precise to the thousandths place, precise to the hundredths place. So within that parentheses, I can only be as precise as to the hundredths place. It would have been 19.15, I believe. 19 point, what does it actually turn out to be? Anyway, because of rounding to the hundredths place, we'll just leave it at that. Because of rounding to the hundredths place, 19.195 is what I think it was, we had to round it up to the 19.2. And then 19.2 minus 3.8, again, for precision, it's to the tenths place now, because subtracting the 3.8 is only precise to the tenths place. 19.20 minus 3.8 comes out to be 15.4 rounded to the tenths place. Somber group, not quite epiphenal. Okay, so are there any questions on practice problem number 1 or number 2? They're basically the same process of just figuring out what the unknown variable is by knowing that the left side is equal to the right side in terms of mass. No questions. Okay. I'll believe you. I'll believe you. Practice problem number 3. Identify the following as metals or nonmetals. So you're given 4 different elements. The first one was bromine. And where do we find that at? Well, bromine is right over there. Okay. So bromine, metal or nonmetal? Nonmetal. And again, for the metal or nonmetal determination, what we're looking at is that stair-step line or that jagged line that separates the metals from the nonmetals. So just very basically, where does it sit relative to that line? Bromine sits to the right of that line, therefore bromine is a nonmetal. Okay. Scandium? It's a metal, right? Again, simply based upon its position in the periodic table. We would expect other things like physical characteristics of malleability, luster, conductivity, things like that, because it's a metal. That's the way we would physically test it. But looking at the periodic table, we can determine it as well because of where it sits relative to the jagged line. So scandium is a metal. Phosphorus. Sits over here. It's column 5 element. Row 3 sits to the right of the jagged line. It's a nonmetal. And lastly, we're looking for radium. Radium is right down here, second column, left of the jagged line, and radium is a metal. Okay? So I'm going to just do this after every question, and I'll believe you if you, by not answering, you're saying no, there's no question. So are there any questions? Yes, ma'am.
Will we have to memorize where they are on the periodic table, like for the test?
No, you will always have a periodic table provided to you, and I don't plan on taking that down. That'll stay up on the wall all year, so you're kind of get used to seeing that. If we do get a whiteboard in here, it may move, but it's going to be up someplace. Generally, what I do is make a paper copy and print it on the back page of the exam. So if in doubt, look to the back of the exam for a periodic table. It won't be this one, it'll be the one from your book. All right. Lacking any questions, any more questions, we'll go on to practice problem number 4. In an experiment to make hydrogen peroxide, a chemist mixes 40 grams of hydrogen with 40 grams of oxygen, and she finds that 42.6 grams of hydrogen peroxide are produced. In addition, a lot of hydrogen is left over at the end of the experiment. How many grams of hydrogen should have been added to the 40 grams of oxygen so that there would be no leftovers at the end of the experiment? Hopefully you see or you recognize this as we're trying to find out what the perfect recipe is. In this experiment, the chemist has put 2 ingredients into the oven, and when she pulled out the brownies, there was something sitting on the top. They didn't mix perfectly. This isn't the perfect recipe. 40 and 40 is not the perfect recipe. So hopefully you're saying 40 grams and 40 grams, well, it should produce 80 grams of hydrogen peroxide, shouldn't it? No, because that's not the recipe. And in chemistry, it's going to make the perfect recipe for the product and then kick back any extra ingredients. So remember, the trick on these kind of problems is to find out how much extra you had of something and then just not put it in. I mean, I hate to be redundant and repetitive and repeat myself a lot, but do you get that? I'm repetitive and redundant and repeat myself a lot? Okay. Keep up. It's like I work for the Department of Redundancy Department, okay? the perfect recipe here is something that we need to discover, and we discover that by looking at whatever was not used up and what was kicked back. You throw it into the system, it gives you your perfect recipe, and then it spits the extras back on you. We don't want to be spit on, right? Let's get rid of whatever was extra. So when we do this process, we're going to find out what was extra, and then what are we going to do? Because right now we don't have a perfect recipe. All we did, we're kids just throwing stuff together. And we just came up and said, I'll take 40 of this, and throw it together. Poof. And God, in chemistry, says, okay, I'll make this much of that for you, and poof, here's the leftovers. Oh, well, if I don't want to have any leftovers kicked back to me, I need to just not put them in the next time I make it. So let me take whatever was extra and change my recipe so that that's no longer there. That's kind of what we're doing with this problem. If 40 grams and 40 grams makes 42.6 grams of whatever it is I'm trying to make, and I've got extra stuff, well, I could just try it again but not put in the extra. Make sense? I mean, if you're making brownies, you put in 3 eggs and the recipe should only have 2, and when you're done, you've got brownies with an egg on top. Next time, keep one of the eggs out. That's the analogy of what we're doing here. So, 40 grams of hydrogen, 40 grams of oxygen, make 42.6 grams of hydrogen peroxide, and extra hydrogen. Let's figure out how much extra hydrogen we have, and then just not take whatever we did use and cut it down by that much so we don't get any kickback next time. So we can actually use the right recipe. So we need to figure out how many grams of hydrogen we have. How are we going to do that? Subtract what? 42.6 from 80. Okay, so we use the law of mass conservation again, and whatever extra hydrogen we have over here, what it's going to be equal to is the mass of our reactants minus how much we actually produced of the right stuff, right? So whatever we actually put in, we put in this much and this much. Okay, with this much and this much put into the recipe, this much of the right thing came out, and I've got this extra stuff hanging around. Let's figure out what that is and not put it in this recipe the next time we do it. So we figure out that the excess hydrogen is equal to whatever we put in, 80 grams, minus how much of the right stuff we made. And by doing that, we see that 37.4 grams of hydrogen was left over at the end of the reaction. We had 37.4 grams too much hydrogen. So, how much we actually need to make 42.6 grams of hydrogen, again, because all of the oxygen is used up, we're not going to change that. What we're changing is how much hydrogen, because that's what was left over. Remember, we said that oxygen is going to be oxygen is going to be our limiting reactant. It's the thing that's going to stop the reaction because it's all used up. We just need to get rid of the extra other thing. So we determined that extra other thing is 2.6 grams. We have, actually, let me back up just a bit. How much do we actually need? It's how much did we actually use minus how much extra did we have. We actually put in how much? We put in 40 grams, right? How much hydrogen? In the initial recipe, we put in 40 grams of hydrogen. How much extra did we have? 37.4 grams of hydrogen. We had 40, and we had 37.4 too much. So 40 minus 37.4 is 2.6 grams. What this is telling me is when I have the perfect recipe for the 40 grams of oxygen, I only need 2.6 grams of hydrogen. Because I had 37.4 grams too much, I take that too much out of what I actually used and figure out how much I should have used. I should have used 2.6 grams, which makes my perfect reaction, my perfect recipe, if you will, 2.6 grams of hydrogen, not 40, with all 40 grams of oxygen to produce 42.6 grams of H2O. Now, this is a long way to go about this. After a while, this will become obvious to you, hopefully, in that I say, okay, all of this was used up. 40 grams of oxygen was used up, and it produced 42.6 grams of this. How much of this did I need? 42.6 minus 40 is 2.6. It'll be more obvious to you then, but this is kind of the long way of going about figuring out how much extra hydrogen did I have, taking that extra amount out of what I actually used the first time, and figuring out how much I should have used, and writing that down now as my reaction equation. So we can say 2.6 grams of hydrogen and 40 grams of oxygen react to produce 42.6 grams of hydrogen peroxide. And again, you might not know that hydrogen peroxide is H2O2. It is, but so, however you wrote it down where you're at now, I accepted it. Looking for that, driving to that point where you can tell me the final formula. This is how much the chemist should have used so as to have no leftovers. Helpful or harmful? Do you understand it better now or less now? Better now? There's a lot of, right now you guys are all very seriously faced, okay? This is not like a typical, hanging out in class, kind of being a little bit lighthearted and everything. Everybody is very somber right now. So it's hard for me to tell the difference between taking it very seriously, being confused, wrestling with what you thought. Those all look kind of the same from up here. So I need some feedback like, oh, that's not quite epiphanal. That's like, yeah, I get it. But you're all looking very serious. So, and seriousness is good, but panic is not good. And I know that because I'm dealing with a little bit of self-induced panic in my life right now. So I'm trying to work past it, and hopefully you are too. So we good with number 4? General bubble? Yeah? Okay, good. Number 5. In making calcium nitride, so you can actually write the formula for that now, right? It's got calcium in it. It's got nitrogen in it. It's ionic because it doesn't use monoditri or anything like that. Anyway, in making calcium nitride, 100 grams of calcium plus 100 grams of nitrogen makes 152 grams of, grams of a product, it says, along with some leftover nitrogen. How much nitrogen and calcium should be added to make 1 kilogram of calcium nitride without any leftovers? So we're making calcium nitride. Okay. We have to make 152.5 grams of it for this formula to be right. But it's not right because we've got extra nitrogen. So just like the last question, we're going to figure out how much extra nitrogen we had and remove it from the recipe that we tried to get the right recipe. So again, law of mass conservation tells me that 200 grams produces 152 grams plus how many grams? And that's 47.5 grams. So I have 47.5 grams too much nitrogen. Okay? We good so far? And this is pretty straightforward, I hope. We've got 47.5 grams too much nitrogen. So how much nitrogen should we have? Okay, we get that by doing what? No, you're good.
Yeah, subtracting the 47.5 from 200.
Well, we're going to subtract the 47.5 from the initial amount we used of that element, right? We have 47.5 grams too much of nitrogen. And we started with 100 grams of nitrogen. So we need 52.5 grams of nitrogen. Why? Because 100 is 47.5 too much. Okay, so what's 100 minus 47.5? 52.5. Okay, now we're going to carry that down and say that we should be 100 grams of calcium then. Forgot the grams, apologize. Unitless number. But 100 grams of calcium and 52.5 grams of nitrogen then produces 152.5 grams of calcium nitride. Okay. Again, this amount of product stays the same. If we just remove the excess from the original, the numbers are going to work out correctly. 100 plus 52.5 is 152.5. Boom, it works, the law of mass conservation. Okay, but now we weren't told to make 152.5, were we? They asked for a kilogram. So we go ahead and say the formula we've just come up with, and I carried that over, so my grams will probably be missing the rest of the way. It's hard sometimes because I try to get the whole thing in one line, and then sometimes I put spaces between the plus signs. Sometimes I can't to get it on the line. I type things over and over again, try to make it look the clearest for you, and typos happen, so I apologize. But 100 grams of calcium and 52.5 grams of nitrogen gives us 152.5 grams of calcium nitride. But we weren't asked for this recipe. This is a recipe that makes a dozen, but we were asked for 50. Well, not really. This recipe gives us 152.5. We were asked for a kilogram. So if we have a recipe that makes 152.5, but we need 1,000, how many batches do we need to make? The X factor here. I put it in terms of kilograms because I was told to make 1 kilogram. And I have a recipe that'll make 152 grams, 152.5 grams, which would be 0.1525 kilograms, right? So if I divide kilograms by kilograms, 1 divided by 0.1525 gives me 6.6. That 6.6 is how many batches I need to make. If I make 6.6 batches, and each batch will make 152.5 grams, I will have 1 kilogram. Now this is the dimensionless unit here. There's kilograms divided by kilograms, no units. It's just a number, it's a multiple. We need 6.6 of the perfect recipe, we need 6.6 of them. So we take 6.6 times the perfect recipe, 6.6 times 100, and 6.6 times 52.5. That produces 6.6 times 152.5, which we already know is a kilogram. Okay. And we do the math. Just multiplying here, 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 and here. Now you may have written it this way. That's fine. But it's difficult. We need to make sure we account for the appropriate number of significant figures. Okay. So 6.6 times 10 to the second grams of calcium and 3.5 times 10 to the second grams of nitrogen produce 1 kilogram of calcium nitride. Or using the units of kilograms, we can write it that way, right below it. Okay, but again, the takeaway here, the big principle is conservation of mass. I've got too much of something, so in order to get rid of it on the left side, I need to get rid of it on the right side. I subtract whatever element I had excess of, I subtract it from however much I used in the first place, and that gives me a perfect recipe. That perfect recipe will produce a batch that is a certain amount. If I need something other than that amount, I need to figure out how many times of that batch. Do I need 2 batches, 3 batches, 5 batches, a half a batch, a quarter of a batch? And then only put in in that case, put in a quarter of every element to produce a quarter of the product. 10 times of every reactant to produce 10 times the product. Okay? Because I want to produce exactly the right amount. And I don't change the ratio in the recipe, because if I change the ratio, that's why to produce 1 kilogram isn't 500 grams and 500 grams. Why? Because the recipe is actually 100 to 52.5. You see that it's almost half as much nitrogen as calcium by mass. So if it were perfectly half, to make, okay, I could make, if this was 100 and this was 50, that'd make 300. If I double it, 200 and 100 to make, 150 make 150, 200 and 100 make 300, and so on, multiples of the same batching. Here it's 100 grams calcium and 52 grams nitrogen that produce 152.5 grams of my product, calcium nitrate. And so that is your answer. 2 different forms right there. The dreaded question. Are there any questions? Okay, you're on tape not having questions, so this is my proof, right? You were given opportunity. How many, I almost do this occasionally, blind survey, close your eyes. How many people in here don't have a clue how to do this? Okay, open your eyes. Let's move on. Nobody doesn't have a clue. Is that a double negative? Means everybody has a clue, right? if nobody doesn't have a clue. Everybody has a clue. They may not have it be proficient, but they all have an idea. Some of these are easy. We'll push through these pretty quickly. What's the chemical formula for a molecule that's made up of 12 carbon, 24 hydrogen, 10 oxygen, and 2 sulfur atoms? What does that look like? Yep, if we do it in order, and they'll generally give them to you in the order they want to represent it, all we're going to do is take those same chemical, out of those same symbols. So I wrote it as carbon, CHOS. You might not have known that. You might have wrote carbon, hydrogen, oxygen, and sulfur, but by now you know the symbols for each of those. So as you look up there, hopefully you're seeing carbon, hydrogen, oxygen, sulfur, because you're associating that symbol with that element. Well, when we name it, when we write out the formula for it, we just simply take the count and we subscript it behind the element. Right? So C12H24O10S2. That's the formula. 7 asks, how many total atoms are in one molecule of this monstrosity? Now hopefully you're seeing that what this means is I've got 3 atoms of carbon, 6 atoms of hydrogen, 12 atoms. This is a typo, isn't it? Another typo. C3, oh, that's the way they did it in the book. Okay, C3H6C12O. You don't normally see carbons 2 places like that, right? But in any case, let's assume that this is correct. So it's 3, 6, 12, and 1 that add up to 22. So anytime you have the formula for a molecule, all you have to do is go through and count up the subscripts, with the exception of, for example, up here, the oxygen at the end. You've got to remember that that's a 1. There's an implied 1. You don't write the 1, it's there. So when you add it up, it's 3 plus 6 plus 12 plus the implied 1. If you put it down as 0, what you're saying is every element that's not there needs to be listed at the end. So you might as well start at hydrogen, helium, lithium, beryllium, barium, start listing them all. Because if that's a 0, then you need to list every element that's not there. We choose rather to say I'm only going to list the things that are there. And since it is there, there needs to be at least one of them for there to be something there. And so everything has at least 1, therefore oxygen has 1. And don't bother to write the subscript. If it's other than 1, boom, we write it in there. So probably the most common mistake here would be to go 3 plus 6 is 9 plus 12 is 21. And that will be one of the wrong answers probably on the multiple choice exam for a question like this. A wrong answer would be 21 to see if you remembered that the oxygen has an implied 1 beside it. We good? Got it? All right. 8 and 9 together. Which of the following molecules are covalent? And then, for number 9, we have to name them. Name these molecules. So for this, we have to know both how to determine if it's ionic or covalent, and then based upon whether it's ionic or covalent, know how to name it. So the first one here, C2H6. Is it ionic or covalent? Group answer, no individuals. It's covalent. Why? There's no metals. These are both nonmetals, right? Oops, I got the name together. So we'll name it after we'll determine it and name it in one step. So C2H6, it's covalent because they're all nonmetals. There is no metal. If they're a metal, it should lead. So check the first one. If it's not a metal, you're probably good, but I check them all anyway, just in case something's amiss, right? But they're all nonmetals, so it's covalent. So which naming paradigm am I going to be using? One that use the prefixes, right? So knowing that, now I go back and I name this thing. So the first thing I'm going to say is something related to carbon. Look at the subscript to create the prefix, and it's going to be a. So dicarbon. Then I look over to 6. Dicarbon hexahydride. And for those of you that wrote ethane, good Google. There are some of your classmates in here know that C2H6 is ethane, but they didn't name it dicarbon hexahydride. They named it ethane. It's correct, but there's no way, unless you don't belong in this class, that you would know that. Right? There are a couple good Google finds when I graded the homework. Next one, pH 3. You're saying it's covalent because? Okay, anybody find a metal in that? Nope. So it's covalent naming paradigm again. First element is phosphorus. Its prefix would be a mono, except we drop the leading monos. So it starts just simply with phosphorus. Then we looked at the next element, looked to the subscript. It's a 3. The prefix then is a tri, and it's the last element, so it gets the ide name. It is phosphorus trihydride. BES. Ionic or covalent? Correct. It's ionic because beryllium is a column 2 element, row 2. Column 2, row 2, Be. It's a metal, which means we don't have any prefixes, right? We just, the first element followed by the second element with its ide name. So BES, beryllium, and element is sulfur, has an ide name of sulfide, and so the element or the compound is known as beryllium sulfide. And the last one, Li2O. Ask the question, ionic or covalent? Ionic, because lithium is a metal. So I take the first element, then the second element with its ide name, and just say it left to right, lithium oxide. Questions? Questions on how to determine if it's ionic or covalent. Okay? The way to determine if it's ionic or covalent is not, as someone said, drop a battery in water and see if it conducts electricity. You don't drop the battery in water. Don't do that. You take a battery, you take 2 electrodes from either end, and you put it into the water. You mix something in it to see if it conducts. Don't put the battery in the water. But we're not asking so much about testing it. Is it malleable to see if it's a metal and if it has a metal in it? See, remember, this is a compound we're talking about here, not an element. And the way we determine if it's ionic or covalent is if it has a metal in it, because if it's ionic and we put it into a solution and mix it up, it'll separate and form ions, and it's those ions in the water that conduct electricity. Right, so 2, 8, and 9, we're good? Everybody? All right. Number 10, what are their chemical formulas? Tetranitrogen hexahydride. We'll start by asking, what are the elements that are involved? Look at this, separate the prefixes out, and look at the second parts and look for the element names. So the first element here is a nitrogen, right? Yeah, you guys are soft answers, so I don't mind if you just answer. So some nitrogens and some hydrogens, right? We've got a certain amount. So we've got, how many nitrogen do we have? Tetra means 4, and hexa means 4 and 6. So we have 4 nitrogen and 6 hydrogen. And then to write it appropriately for the formula, we take the count and we make it the subscript. So the 4 nitrogens and the 6 hydrogens looks like N4H6. Tetranitrogen hexahydride. And the second one was dihydrogen monoxide. First element is hydrogen. How many of them? And the second one is? And how many? Okay, so 2 H's and 1 oxygen is water, H2O, dihydrogen monoxide. Now this goes back to that idea of a common name. Remember, the common name for dihydrogen monoxide is water. From now on, maybe in class we should say, hey, Mr. Baker, can I go get a drink of dihydrogen monoxide? Common names are no longer allowed in here. So ethane, no more. We've got to give the chemical formula for it. Or water, can I go get a drink of dihydrogen monoxide? No, we're not going to do that. That's what we have. We have common names that we use all the time, like ethane, right? So we don't have to know the full formula, but we use it so often. It's water. And if I said to you, okay, I need 10 grams of water, I would expect you to write 10GH2O, because the common name should be so familiar to you that you could say water. Okay, H2O. You don't write it WATR, you write it H2O. And I say, hey, what do you have there? Water. What's its formula? H2O. What's its chemical name? Dihydrogen monoxide. Good. Okay? Because you don't go to the store to buy bottled dihydrogen monoxide. If you want to be a real geek, ask for it in the aisle and see what the clerk says, right? Hey, where's your dihydrogen monoxide? Chemicals are down there. I want bottled water. I want to go in there and pay for something that I can get out of the drinking fountain or from, never mind. Number 11. Classify as either a mixture or a pure substance. These things. It's a pure substance. Now, before we look at each of those, a pure substance is something where when you have a sample of it, every single structure that you have is exactly the same. If it's an element, well, if it's an element, if you got a sample of an element, that means every atom is exactly the same. And if you have a sample of a compound, that means that every molecule is exactly the same. But if you have something that has different things mixed together, then we call it a mixture. Okay? So the question here, is it a mixture of things, or is it a pure substance of things? Is everything in your hand identical, or does it really represent different things beside each other? So, soil. Pure substance or mixture? Mixture. Is there an element known as pure soil? No. As soil over there. It's not on a periodic table. Can we take atoms and build up a molecule known as soil? Hey, can I have 2 molecules of soil? No, there's no such thing. It's a mixture of things that make up soil. And you know that if you're a gardener, you see what your soil has and doesn't have, and you add to it, you amend it to make it what it needs to be. Okay, so that's the idea here for mixture. Silver. Pure or mixture? It's pure. If you have silver, then every atom in your hand is the same structure. It's the same atom. If I go to the periodic table, is there an element known as silver? Yes. So it's pure. It's a pure substance. Nitric acid. HNO3. Is it a pure substance or a mixture? Survey says it's a pure substance. If I have a sample in my hand that has hydrogen, nitrogen, and oxygen in it, and they're individual atoms, I have a mixture. But if the hydrogen, nitrogen, and oxygen have come together to form molecules of the compound nitric acid, and they're all exactly the same, then I have a pure substance. The pure substance is the molecule HNO3, or the compound HNO3, because I have molecules of HNO3 in my hand, which wouldn't be too healthy because it's an acid and it'll burn your hand. But anyway, you get the idea. It's a pure substance because every single structure in my hand is exactly the same. And lemonade. Caveat here, no pulp. Okay? There's always these little wrinkles, like, and I don't bring up all the exceptions all the time because some of these are just trying to drive the point home. But I'll say lemonade, no pulp, well stirred. It's a mixture because there is no element of lemonade and no molecule or compound known as lemonade. It's elements and compounds mixed together. Okay? And when you put the citric acid into the H2O, it doesn't become something else. It's still water and citric acid and a few other things all mixed together, but they don't react to form a new one thing. They stay themselves, they just get spread around to form lemonade. All right? Now, question 12 has us go through the same list again and decide whether or not these items are elements, compounds, homogeneous mixtures, or heterogeneous mixtures. So whether or not if they're a pure substance, they're going to be either an element or a compound. And if they're a mixture, they're going to be either heterogeneous or homogeneous. Right? So, classify them again. Silver. We said before that it was a pure substance. So is silver an element or a compound? It's an element, right. Oop, I skipped soil. I looked down past it. I gave you that one. A heterogeneous mixture for soil. What does that mean? That everywhere you look in the soil, it's not exactly the same. Soil has layers. Soil is better or worse in different areas, so it's not exactly the same. It depends upon where you look, which means it's heterogeneous. If it was homogeneous, then soil is soil. It's still not reacted to form one compound, but it's the same everywhere, and we know that's not true. Silver is an element because it's a fundamental building block. You can have silver, but silver can't break down into anything else. So it's not a compound, it's an element. Nitric acid, pure substance or an element. Excuse me. In that case, we said before it was a pure substance. Is it an element or a compound? Right, it's a compound. And lemonade. Well stirred, no pulp. Homogeneous mixture. Say the same thing like with iced tea, you know, with the sugar completely dissolved and no little flakes in it. It's kind of like the caveat. It's a mixture, right? But it's the same all the way through. If it's well mixed and there's no pulp, every glass should be the same. It's not like people are fighting to get the first glass or the last glass because it tastes different than the other glasses. It should be the same throughout. Is that a perfect analogy? No. Because if it does have pulp, the pulp settles, then it becomes a heterogeneous mixture, things like that, the caveats. But that's changed till Thursday, but we did actually go through all the practice problems. So what I'd like you to do in preparation for tomorrow is to go through and either questions that you come up with that you still have, or look at the extra practice problems and propose questions that you would like us to do in class so we can do them together. We can kind of nail that again. This is what, this is where you've got the difficulty, and then on Thursday, plan on taking the assessment.